Thanks a lot. Like Mark said, my name's Chris Miles. I'm a freelance iOS software engineer based in Melbourne. Today I want to talk to you about OpenGL ES, particularly with iOS and iOS 5. Bill's talk was a great lead up to this. He talked about the CPU and GPU split, which was a perfect sort of intro for what I'm going to be talking about, which was really taking advantage of that GPU side of things. So let's get straight into that. I'll first just describe what OpenGL ES is for those who aren't familiar with it. So it's an open standard for 2D and 3D graphics programming. It's not Apple or iOS specific. It was invented by Silicon Graphics quite a while ago now and is used on a lot of different systems. It's typically hardware accelerated by the GPU. On iOS devices, that's the case. So we've got a language that we get direct access to the GPU. It's probably the lowest layer of graphics programming we can do when we need that raw performance. It's a cross-platform and C-based API. And the ES part of OpenGL ES is the embedded systems variant as opposed to the desktop version of OpenGL. So the embedded systems variant is kind of like a cut-down, more optimized version of OpenGL for mobile and embedded devices. If you've heard about any OpenGL ES, you may have heard of the different versions. There's 1.1 and 2.0 versions of OpenGL ES. Well, we're not going to really talk much about those. We're going to be focusing on 2.0. 1.1 briefly was called a fixed pipeline version of OpenGL. And the analogy I've got really is that, remember the early days of HTML, the really early days, all you could do was kind of specify a couple of attributes on how you want your text laid out or bolded or flashed. 2.0 is kind of the HTML5 modern version where we've got CSS and JavaScript and we get to write code within the browser and modify things on the fly. Since we're targeting iOS 5, we're going to be taking advantage of a new framework that Apple added called GLKit. GLKit adds a bunch of high-level abstractions and convenience classes that allow us to do OpenGL programming much quicker and much more simply than we used to have to do. So we get things like which we'll go into in more detail shortly, GLKViewController and GLKView, this GLKBaseEffect thing and a bunch of math functions. And it makes OpenGL programming so much easier, so we're going to be focusing on using that, which is why we're targeting OS 5 here. So my goal with today's talk is to basically teach you enough of the basic concepts on OpenGL ES programming with GLKit that by the end of the talk we can fire up a project using Apple's OpenGL template that Xcode provides, walk through that, and with any luck you'll understand many more of the concepts in there, what that is actually doing than when you walked in. So you can judge me on how well I've gone at the end of the talk. Right, so first we'll start with the first thing we have to do really is set up a scene for drawing into. And we can do that, again with GLKit, we can do that by using GLKViewController and GLKView. We start by creating a view controller for our scene, and we can create a subclass of GLKViewController, which basically abstracts out the setting up of a timing loop that we used to have to do manually ourselves, and also some interactions with the OS, like when the app is backgrounded or becomes inactive, then the timer's paused, which means the OpenGL rendering's paused, and a few conveniences like that. It also ties into a GLKView, which we'll look more at in a moment. And a GLKView is a really nice abstraction of a view that we can render OpenGL into. We don't have to use a GLKView with a GLKViewController. You can have a GLKView embedded in a normal view controller in a normal view hierarchy. So you can have an OpenGL view basically drawn inside a normal view hierarchy if you like. But when tied up to the GLKViewController, then all the timing loops in place and we get a good pairing there. So I've got a demo application that I'm going to be using to show some of these concepts. Before we fire that up and have a look, I'll just look at some of the basic setup routines that we use to set up our OpenGL environment. If you've ever looked at OpenGL on iOS before iOS 5, you probably walked away when you saw the amount of boilerplate setup code that used to have to be to just set up the whole environment just so you could do the simplest drawing. Well, now that's really cut down using GLKViewController and GLKView. That's cut down to almost nothing, very, very small amount of code. So this is an example of a view did load for a GLKViewController subclass. And the setup routine is really as simple as this for a basic application. What we first do is we create an EAGL context, or an Eagle context, and that's basically a GL context which holds all the state and information about the OpenGL sort of frame buffer and stuff that we're drawing into. So because we're focusing on OpenGL ES2 with GLKit, we'll specify the API version of 2. Then what we do is we pass that context to the GLKView. So we grab a reference to that from the view controller's view, we pass the context across to that GLKView, and then optionally we can also tell the GLKView that we'd like a depth buffer. If we're doing any sort of three-dimensional drawing in the scene, you typically use a depth buffer to help determine which triangles should be drawn in front of the other ones so that your 3D scene looks properly from the point of view of the user. So we set the drawable depth format to one of the properties that enables the format of the depth buffer we'd like. 24 bits is fine. And we can also optionally tell GLKView how many frames per second we'd like to draw. By default, it sets it at 30, but as Bill was mentioning, we don't like to settle for anything less than 60, so bang, we go straight for that. The last thing we do in that method is call our custom setup GL method, which will perform a bunch of OpenGL setup for our particular scene, and we'll look at that shortly. The other two important methods in the GLKViewController are the update and the GLKViewDrawInRect. So the update method will be called automatically by the GLKViewController every time your frame needs updating, so 30 or ideally 60 frames per second. And the job of update, which is code that you supply, is to perform any of the sort of data setup that you need for that particular frame. So you do any sort of transformations, any physics simulations, any other animations and things in terms of the data, get the data ready for the drawing. Then, shortly after that, the GLKViewDrawInRect method will be called. Again, this is 60 frames per second or however much you've got your timer set up for. And that's where you perform your actual OpenGL drawing. And obviously we're going to fill these methods out as we go. So let's sort of just revise a couple of things we've looked at, and then we'll have a look at what that looks like. So the GLKViewController, it implements the OpenGL ES rendering loop for us, and it does things like automatically pauses the rendering loop when the application's inactive or backgrounded. It's the recommended way to support device rotation. The old recommendation for, say, pre-iOS 4.2 was to not do view controller auto rotation because that was not very performant. But these days, Apple have sorted all that out, and it is recommended to use the view controller for auto rotation of your GL views, and it works hand in hand with a GLKView. A GLKView is a UI view subclass that's responsible for creating and managing the OpenGL ES frame buffer object for you. It takes care of a lot of boilerplate code that we used to have to write, so that's a nice class there. And if you're using a GLKView on its own, you can subclass that and do your OpenGL drawing simply by overriding DrawRect and just doing your drawing like you might do core graphics drawing. And it works with the UI view mechanics. You can call self set needs display, and it will tell the call DrawRect as needed. So that's nice. It supports color, depth, and stencil buffers if you need any of those. And you can also switch on the 4x multi-sampling just by flicking a switch if you want that, which is pretty cool. All right, the next thing we need to worry about when we're setting up our OpenGL drawing is the Vertex data. So I'll explain what that actually means as we go forward. But first, let me show you something so you can get an idea of what we're actually aiming for here. I've got just this little demo app, which I'll fire up in the iPad simulator. And what we're going to do is just draw a few triangles. So I've got 8 triangles being drawn there, all laid out on a flat plane, and I've got a bit of transform animation just to spin the things around so it looks a bit more interesting. So we're going to just start off with that basic drawing and have a look at what we need to do to sort of achieve that. So the most complex primitive we can draw in OpenGL ES is a triangle. And we tell OpenGL about triangles by specifying the vertices of those triangles. So for every triangle we want to draw, we tell OpenGL about the 3 vertices that make up that triangle. So in the drawing on the left, number 1, number 2, and number 3 are the 3 vertices for that triangle, and the one below it has 3 vertices of its own. We can draw more complex shapes, for example, a square here, by joining triangles together, and then any more complex shapes, 3D models of any kind, are simply drawn by joining heaps and heaps of triangles together. Typically, you would use a 3D modeling program to do that work for you and export the data. But for simple stuff, you can make up the data yourself once you see how we lay it out. So in terms of code, like I said, OpenGL is a C-based API, and so we're working at pretty much the low level here. We specify our Vertex data by handing OpenGL all the raw data that it needs to do that. But there is some sense to the data, so I'll go through what we've got, what we're showing here. We're just using a static C array to specify that data. You might, in more complex models, you may load that data from disk or load it from a 3D image format and decode it. But however, that's all. Any way you load the data is up to you. In simple cases, we can just have a static C array. And what we've got here is the vertex data for 2 triangles, and each line of the array here, so the 3 values on each line, are the three position values for each vertex. So we've got 1 vertex per line. Each vertex has 1 attribute specified, and that attribute is the position attribute. So we've got XYZ for triangle 1, XYZ for for vertex 1, XYZ for vertex 2, XYZ for vertex 3, and the 3 vertices make up triangle A. And we've got 3 more for triangle B, and that's how we'd be drawing 2 triangles. In this case, they're joined together to make a square. The next thing we have to do is load that data into OpenGL and actually tell it what the data means. So at this point, we're still working with OpenGL direct C-based API. GLKit isn't helping us here yet. We'll get a little bit later where GLKit helps us some more. So this is all still C functions. What we do is we create a few OpenGL objects to help us abstract and manipulate that data. So first we create what's called a vertex array object, and that's an OpenGL object that basically abstracts the vertex data configuration, or it encapsulates that configuration for us. So we can create this object, and then all the rest of the vertex setup functions below it are all basically saved within that object. So then we can refer back to that later just by reactivating that object when we need this particular configuration. So we create the vertex array object by calling glgen vertex arrays OES, and the OES is simply a suffix for an extended OpenGL function, or for an optional extension, but that's not too important. So we first ask OpenGL to generate an identifier for that object, and we tell it we want 1 identifier. We can create multiple at once if we want, and we give it a variable, the address of a variable, to return that back to us. We then bind that identifier by calling glbind vertex array OES. So this gen and bind pattern we'll see fairly commonly in OpenGL, where we also ask OpenGL to generate an identifier for a particular type of object. And these aren't NS objects, these are objects within the OpenGL system. And all we get back is the identifier. OpenGL will manage those objects for us. And when we want to use an object, we bind it and it becomes the active object for that type. So the next thing we do is create another OpenGL object. This one is a vertex buffer object. This object is responsible for keeping a copy of our vertex array data. So that C array we saw before, what we're doing is creating an OpenGL object that will store that in sort of GPU optimized memory somewhere so that we can refer to it when we need to. So again, we call the gen and bind pattern, glgen buffers, glbind buffer, and we tell it we want a buffer object of type array buffer, which is the type that you put in vertex data arrays. Then what we do is we give OpenGL a copy of that data to load into that buffer. So we call glBufferData, and we give it the size of that data array in bytes. We give it a pointer to the data for it to copy it all from, and we then give OpenGL a hint on how we expect to use that data. In this case, I've specified GL dynamic draw, which tells OpenGL, here's a copy of the data, but I'm actually going to be modifying it later because I'm going to be animating some of the vertices and moving things around, we'll see that shortly. If you're loading in a 3D model, but you're not actually going to be modifying it, you might specify GL static draw, which means here's the vertex data, I'm not going to be modifying this, you store that in the most optimal way that's maybe sort of close to within video RAM or whatever's relevant in that particular system. The last thing we do, it seems like a complex step, but it's the low level, so you just sort of learn this once and it's pretty simple from then on. We have to tell OpenGL how the attribute data is laid out within that vertex array. So in this case, we have one, as we saw here, we've got one type of attribute which is position, x, y, z for each vertex. So here we tell OpenGL, for that data I've just given you, this is the attribute types we've got. We've got a position attribute, and the position attribute is laid out in this way. So the very last line, GL vertex attribute pointer. For the position attribute, we've got 3 values per position. They are all floats, and we'll set the rest of the arguments to 0 because we won't worry about them. We'll use the defaults for now. We'll look at those later. So sort of just to revise on what we looked at there, we first created the vertex array object, which is an OpenGL object for encapsulating a vertex data configuration for us. And it allows the OpenGL driver to optimize that state in a way and save it for us. And they're the function calls relevant to that. We then created a vertex buffer object, and that is responsible for storing the vertex data in some GPU optimized memory. It's an optimization that avoids, for example, say copying the vertex data in every draw frame, which might be the default way that you could do this thing. You could do this type of vertex loading. And there's the function calls for that one. Then the last thing we did was enable and configure any attribute data that we were giving OpenGL as part of that vertex data. One thing to note when we're using GLKit is the attribute indices. So the sort of the first argument is we should use the ones provided by GLKit, the constants provided by GLKit. So we use GL vertex attribute position, and GLKit provides attribute indices for normal, color, and texture coordinates. Okay, so moving on, we've set up our scene with the GLKViewController and GLKView. We've loaded in some vertex data, so we've told OpenGL about some triangles that we'd potentially like to draw, but now we should actually get on with drawing something. So what we're going to use is a GLKit class to help us draw, which makes things a lot simpler than it used to be, called GLKBaseEffect. So what I'm going to do is switch back to my demo app. We'll look at the triangles demo again. What I've done is added a feature to the demo that if I tap on the screen, then it animates all my triangles into this sort of 3D box shape. So a box with an open top and bottom face. And all the triangles are, so the triangles are obviously joined together to make a face for each side of the box, and we've got 4 faces to create that box. And we continue rotating that around the screen. So in terms of how we go about drawing that effect, what we do is we create an instance of this GLKBaseEffect. Now, a GLKBaseEffect is basically a GLKit abstraction for writing shaders for us. So in the simple sense, before GLKBaseEffect, or if we didn't want to use it, we would have to write what are called shaders, and those are some user-supplied programs that run on the GPU that determine how our vertices are laid out and how they're coloured and all those sorts of things. And that's a topic in itself that we're not going to go into today. And one reason we don't have to go into it is because GLKBaseEffect is a class that will actually write the shaders for us. We tell it what effects we want when we're doing our drawing, and then it literally compiles and loads the shaders in and executes our code on those shaders for us. So we create an instance of that somewhere in our setup part of our scene, and then when our update's called, we can update any parts of the GLKBaseEffect that are relevant to that particular frame. So in the simple case, we want to set the projection and model view transforms of this scene. The projection matrix defines how the triangles are drawn onto the 2D plane, so how they're projected onto a 2D plane. Basically, you're setting your perspective of your view. Think of it like choosing your camera lens, whether you want a wide lens or a narrow sort of lens. And your model view matrix determines how that particular, those triangles are transformed in that scene. So whether they're rotated, scaled, and so on. And you supply, we don't show the matrix calculations here, but you calculate matrices the same way that you do for like, core animation matrices and so on. But actually using GLKit functions, so we'll see those. Then in our draw method, we'll fill that out. So GLKView draw in rect. To simply draw the data, there's only a couple of lines we actually need to do because we've already set everything up. So the first thing we do is we clear the color and the depth buffer with the first two function calls. Then we tell our GLKBaseEffect, we send it the prepare to draw method. And what that does is if GLKBaseEffect needs to, it compiles in the shaders, creates and compiles the shaders, and then makes them active. Or if they're already compiled and it doesn't need to, it just makes them active. And so they're ready to actually render out our drawing. In this example, we call GLBuffer data again to update our Vertex data, because I'm animating between the sort of flat triangles and the 3D box. So we do that by just modifying the Vertex data. So we update those, and then we call GLDrawArrays, and we tell it that we want to draw triangles using all the configuration we've already set up and using the shaders that GLKBaseEffect has loaded for us. Up until now, we're really just, up until GLDrawArrays, we're basically setting up OpenGL state. Nothing's hit the GPU yet. It's not till a draw command like GLDrawArrays that all that's bundled up into a draw request and thrown down to the GPU to actually perform drawing in the background while our application continues on using the CPU. So the GLKBaseEffect, we'll just review that. It takes care of rendering any of the effects for us, and it does that by writing the shaders. It handles things like the projection and model transforms, vertex coloring, texturing, lighting, and even fog effects. And one of its goals is to replicate all the OpenGL ES 1.1 effects. So I mentioned that briefly, where OpenGL ES 1.1 had a fixed pipeline. If anyone had used that and hadn't wanted to go to OpenGL ES 2 because they lost those effects, or they were a lot harder to reproduce, then GLKBaseEffect helps bring those back for you. The next thing we can do to make our demo more interesting is to apply some colors. So we're going to color in our triangles. I'll jump back and fire that up. And I've got this second mode where we apply some color. So the first thing I'm doing here is just applying a constant color across all triangles. If we tap to animate those back into our box shape, then we can see we've got a constant colored box. Because they're all literally constant colored, it's hard to see that sort of depth effect in the box, as you can see, but that's something we can look at shortly. If we go back and switch to what I've called vertex colors, then we've got a much more interesting color effect, and we can throw that back into a box, and it visualizes much better when all the faces of the box are different colors. And what we're doing here is we're simply setting, we're adding an extra attribute to each of the vertex data. Along with position, we're adding a color attribute. So we're specifying for each vertex of each triangle, this vertex is this color, this one's this color, and this one's this color, and so on. And by default, the GPU will interpolate the color across the face of the triangle and sort of fill in the rest with that gradient. So that's a handy way to get a quick effect. So to actually enable the effects, we can use GLKBaseEffect to apply constant color if we want one. We do that by just setting the constant color property to any color we like, and we can enable the use constant color flag, and that will apply that particular color to every vertex in the shader that it writes for us. Alternatively, if we're supplying our own colors with the vertex data, like I described, then we can just simply switch on that attribute as part of the vertex data configuration. So we enable the color attribute, and then the shader's already set up to use that if it's there. An optimal way to give OpenGL the multiple attributes for each vertex is to interleave those. So as an example here, we've got the position XYZ like we saw before, but then we follow that, for each vertex, we follow that immediately by the red, green, blue alpha values for the color. So for each vertex, we supply the XYZ, RGBA, and so on. That allows good memory locality, so for each vertex it's processed, all the actual raw data is close together. Alternatively, you could specify different vertex arrays for each of the attributes, but this is the recommended way to get better performance and pretty easy to set up out of the box. One convenience I like to do, which isn't necessary, but when you're dealing with basic C arrays, is to set up a struct to help abstract access to that array. So here I've just set up a simple struct with the position and color parts separated. So when we're accessing a part of the vertex array, because for example, if we want to modify some of those vertex positions like we do in our animation, we can just access that by the structure parameters. So we've got, within our struct, we've got 3 floating point values for the position, then 4 unsigned bytes for the color values, and that makes things a lot easier when we're manipulating that data, and also when we're calculating byte offsets, which we need to do to tell OpenGL about that data, which we'll see in a moment. And here it is. So when we add a second attribute, we do what we do before. We had the position attribute, and then we enable that attribute, and then we tell OpenGL how that data is laid out. So 3 floats. We specify the 4th argument is false. I'll describe that in a moment, but we give it something called the stride. And the stride is basically the amount of bytes between each vertex in our data array. So we supply that to any of the attributes that are part of that particular vertex. So the color one at the bottom, we enable that and tell OpenGL there's 4 values for color, and they are all unsigned bytes. The 4th argument we set to true, and that enables normalization of the data. So the 0 to 255 values that we'll get as part of a byte, they are converted to a 0 to 1 automatically by OpenGL for us, which is more useful for what the shader is expecting when it's doing its calculations. Again, we give it the stride, and then the last argument is the byte offset of that particular attribute within the vertex data. So all this is pretty dry, I know, but we've got to deal with setting up raw data and telling the OpenGL how we actually want to draw, how that's laid out, so then we can actually get on with drawing. So we'll get on to something slightly more interesting, which is applying lighting to our scene to get a more interesting, I guess, realism. So I've added a 3rd variant where we've got some lighting enabled. So we've got our same constant color applied, and if we transform that into our sort of 3D open box, then we can see we've got a much better visualization. The different faces of the box are shaded depending on their orientation to the light source, which in this scene happens to be sort of directly behind us. And we get away with using constant colors if we like. If we switch to the vertex colors, we get the same effect applied, both the colors across the face, but the lighting's applied. We can sort of switch that on and off to see that that actually makes an effect. Once again, our friend GLKBaseEffect does all that for us. So it will support up to 3 lights in one scene at one time. We'll just use one of those. So we pick light 0 and we enable it. Then we set some properties of that light source. The first thing we do is set the ambient color, and that's sort of basically the non-directional background color of that light source. I like to think of it, say you're in a room in the house with the lights off, that'll be like the ambient light within that room. If you then switch that light on, and so there's a light source within the room, then that's the diffuse color, equivalent of the diffuse color, the next property here. So you're saying what the actual directional light, what the properties of that light source is. Then what you need to do is tell OpenGL the position of that light within the scene, and the position property is how it's used depends on what sort of light source you're using, and the type of light source you're using depends on the 4th value in that vector for position. So here I've set the 4th value to 0, and that means a directional light source that's infinitely far away. So kind of the equivalent of, say, sunlight, where all the light rays are parallel to each other. If you set that to a value greater than 0, then that indicates a spotlight or a point light, depending on how you set it up, and the position would be the position of that spotlight or point light within the scene. The last thing we do is enable the 2-sided model lighting. So by default, OpenGL or the GLKBaseEffect will take the optimal path and only light the front face of triangles. That's commonly what you want in a 3D model where you can't see inside the model. But in our case, we can see inside. We can see the inside faces in our open box. So I enabled two-sided lighting, so it does more work to apply calculations to both sides. In a very oversimplified diagram, this is one of the things that the light calculations are trying to do is to determine the angle of the light source as bounced off that particular triangle, and it does this by using what's called a surface normal. And the surface normal is a vector that's pointing perpendicular to the face of the triangle, and how we supply that to OpenGL is by supplying the vector normals for each vertex that we're passing in for that triangle. So we can demonstrate that by showing our vertex structure again, where we've got our 3 floats for position XYZ, then we specify 3 more floats for the normal vector, which will be in XYZ, and then we have our color data, the RGBA. So the GPU can interpolate the normals across the face of the triangle if it needs to, and then that can determine the surface normal for us. Right, the last thing before we have a look at the template code that I want to just have a look at is really just the high-level view of where shaders fit into things and the inputs and outputs of shaders. We're not going to look at shader programming at all because it's a massive topic on its own, but we also don't really need to. But we just want to touch on just enough to get an understanding of what goes in and out of these shaders for when we look at the last bit of code. So starting at the left, what we've got are the vertex attributes that we've been talking about during the talk. These are really the inputs to the vertex shader. And the vertex shader is responsible for really transforming any of the vertex data into the form necessary for the rest of the pipeline. For the vertex positions, it's responsible for applying the transform, the projection transform, so basically projecting those vertices onto the 2D plane. And it can also perform anything else because they're programs that we give it if we are writing it. They might perform the lighting calculations per vertex or anything like that. The outputs of the vertex shader that we want to pass to the fragment shader that I'll talk about in just a sec are called the type of variable called the varyings. And these are something you define as you want to output that from your vertex shader. They get linear interpolated by the GPU across the face of the triangle as the triangle is being prepared to be rasterized, and then they are input to the fragment shader. And so the fragment shader is the second stage of this simplified pipeline. It's responsible for basically setting the final pixel color of the frame buffer for that triangle. So in simple cases, it might just pass the colors through. In other cases, it may apply lighting or texturing effects or anything else. The other variable type that we need to know about are called uniforms, and they're effectively global variables that are made available to both the vertex and fragment shaders. So they're commonly things like the projection transform, which is only sort of set up once for a particular draw call. The final output of the fragment shader is the data written to the frame buffer that's then made available to core animation to composite and render to the screen, like what Bill was talking about. So on iOS, the final output of the fragment shader isn't drawn directly to screen like it is on some systems. It's drawn to a frame buffer, and core animation actually handles the screen presentation. All right, so just sort of revising those things on shaders. The vertex shader performs the vertex calculations, for example, projecting vertices onto the 2D plane, and it executes a shader program that we give it once per vertex. The fragment shader receives interpolated values from the output of that vertex shader. One of its jobs is to calculate the output pixel colors, and it is executed once per output pixel. So with that sort of lightning overview of some of the concepts in mind, let's have a look at what the OpenGL template gives us out of the box, and we'll see how much our new knowledge helps us understand what's going on in that. So I'm going to create a new project, just choosing OpenGL Game, which is the OpenGL template project that we get. And I'll just call it GL Game, and we'll just leave everything default. We'll use storyboards and arc. And we'll throw that there on the desktop. And we'll just have a look at what we get out of the box. So if we run that, what we get out of the box is a simple scene with two 3D cubes. They're orbiting around each other and they're being rotated themselves. They're coloured differently, different colours, and they also have lighting applied. So that's not a bad starting point for a 3D scene using OpenGL. So let's just jump over to the code and have a look at how they're doing that, using all that knowledge that we hopefully learnt really quickly just then. Starting at the app delegate, there's nothing particularly special here. They've got a window property, and let me just open that. In the implementation, it's all pretty much empty given they're using storyboards, so there's not much to see there, but it's all very standard. If we have a look at one of those storyboards, we've got a view controller, which is a class of CMViewController up on the right. We'll have a look at that in a moment. But one thing to note is the view is of a class of GLKView. So they've wired up a GLKView directly to the view controller. Just looking on the left, we'll skip they've got some shader programs here, which is interesting, but we'll skip those for now and come back to them. We'll jump straight to the view controller itself. So the CMViewController is a subclass of GLKViewController. So it's all set up out of the box to use GLKit, which is good. And then looking at the main implementation file, which is the bulk of where this project actually has some interesting stuff. They've got a macro to help with calculating offsets. There's nothing exciting there. What they use as a convenience is a couple of enums to help define the identifiers for their uniforms and for their attributes. So as we saw when we sort of had the high-level overview of shaders, the uniforms are the global variables that are made available to the shader programs. So they track the identifiers in these enums and a little array for those, and they track the attributes that they're using for their vertex data as a couple of enums as well. Then they supply all the vertex data for their cube as a C array. So similar to what we saw before, they've got a vertex per line with two attributes per vertex. The position XYZ, then the normal vector XYZ. So they've got 3 vertices per triangle and 2 triangles for one face of the cube. And if we go down, there's 6 of those grouped together, so the 6 faces of one cube. So that also tells us they've only got vertex data for one cube, and they're drawing 2 cubes, so they're repeating draw calls for the second cube. So we'll see that shortly. In their IVARs, they've got a couple of these GLU ints for some of the variables. These are where they store the identifiers for any of the OpenGL type objects. So they've got a vertex array and vertex buffer objects, and they've got an identifier for the OpenGL, for the shader program that they load in. Then they also use some of the GLKit math types, GLK matrix 4 and 3, or 4x4 and 3x3 matrices that GLK math supplies to us. GLK math supplies a load of different things which are useful for this type of programming, and if you've got any math code from any other OpenGL programming, it's worth probably using these ones instead. There's a bunch of convenience functions for doing calculations and multiplications on all those, as you'd expect. They've got a couple of properties for one for their eagle context and one for their GLKBaseEffect. So it's obvious that they must be using both their own shaders and GLKBaseEffect. So we'll see probably why they're doing that down here. But first we'll just check their view did load. Pretty much looks exactly like our one, although they're not specifying 60 FPS, so Bill wouldn't be happy with that. The view did unload tears down some of that. We'll skip through that. Should auto-rotate and memory warning. It's all standard stuff, so there's not much there that's different to normal until we get to some OpenGL specifics. So here they make sure that their eagle context is the current context, and that's how you do that. It is possible to have multiple EAGL contexts. They call their own load shader method, which sets up their shaders. We'll glance at that in a moment. Then they create their GLKBaseEffect. So they're enabling one light source, and they're setting the color of that light source and leaving all the other properties at their defaults. They enable the depth testing function. So they're drawing 3D objects in their scene, so they need proper depth testing to handle triangles being drawn in front of triangles that are behind. And then they do similar to what we had with setting up the vertex array object, vertex buffer object, and then loading in or configuring the attribute data for their vertices. Their teardown basically reverses all that, and then we get to where they actually start to set up and perform their drawing. In their update method, you can see there's basically a whole lot of matrix calculations to set up their transforms. They set up their projection matrix by using, by using probably that button. GLKit convenience function, GLK matrix for make perspective, which is just a handy way to define your perspective of how you want that 3D drawing projected onto the 2D plane. And you see there's other GLKit functions like GLK math degrees to radians and so on. They set that to the GLKBaseEffect transform property. They do some calculations for their model view matrix, which we just skip through. You can study that at your leisure. Then they do some, and they set that to the GLKBaseEffect transform model view matrix. Then they perform some more model view matrix calculations for their second cube, and they store them in the IVARs. Then in the actual drawing function, they clear the buffers like we saw before. They make sure their vertex array object is the bound one. It probably would be in this case, but it's good practice to, usually you might have more than one vertex array object, so that's how you enable the one you're working on at this time. They tell the GLKBaseEffect to load its shaders and prepare them ready for drawing. Then they call GLDrawArrays to draw the triangles for the first cube. Then what they do is they switch to using their own OpenGL shaders. They've loaded them, which we'll see in a minute, but they use the identifier for that with GLUseProgram, so that switches to their own shaders, and they load in two uniforms. So the IVARs of the model view projection matrix and the normal matrix that they calculated before, they pass those through to the two uniforms so that they're made available to the shader functions. Then they do the exact same GLDrawArrays call to draw the triangles for the second cube. Lastly, the rest of this file is really all the sort of boilerplate code to load in these custom shader functions. I'm not going to look at that in any detail, but they've got stuff for compiling, linking them, and so on. You can basically, if you're doing any custom shader program, you can copy that code as it is and reuse it. What we will do is just finish up by glancing at the shader programs, just so you can see what they actually look like. So this is the Vertex shader that we get out of the box with the template project. We can see that from a high level, it's kind of a C-like language, and that's what the shader language is. But at the top, we specify any of the attributes, varyings, and uniforms that we expect to use within that shader program. And you can see they've got some special types like mat4 and mat3 and vec4 for different matrix and vector types. The entry point to a shader is the main function, like C. And so here they've got the actual calculations that will be performed on each vertex as it's been given to the shader. Firstly, they do some lighting calculations on the vertex, and then they apply the result of the lighting to the diffuse color of that particular vertex to set the final color value that will be output as a varying and given to the fragment shader. So that's an example of per vertex lighting, where the lighting is calculated for each vertex and then interpolated across the triangle, which is a more performant way of doing lighting. It is possible to do the lighting in the fragment shader if you want to calculate for every single pixel, but that will take up more resources. The last thing they do is set the GL position of the vertex itself, so they're basically doing that actual projection onto the 2D plane. And the GL underscore variables are the OpenGL specific sort of output variables, so GL position sets the final position of that vertex. We'll jump to the fragment shader, and we can see there's very little here. They define the varying that they're expecting to receive from the vertex shader, that color vector. And in their main function, all they're doing is just passing that color value straight through to the output color, which is the GL frag color as the output color value for that particular pixel. And I think that's basically it for that program. So that's the template project that we saw. Just to summarise what we had a look at today, we learned a bit about GLKViewController and GLKView and how to set up the vertex data with vertex array objects and vertex buffer objects. We used GLKBaseEffect to draw some of the basic effects we need, and we used that to do some colouring and some lighting, and we also had a real quick glance at the shaders and how they're kind of joined together with their inputs and outputs. So Tomorrow I'm doing a second OpenGL talk, which goes into more advanced things you can do with GLKit, different effects, as well as applying texture. I'll also be going through the OpenGL ES debugging and profiling tools that Apple makes available for us. The debugging tool in particular is extremely useful if you're learning OpenGL, because it gives you such a clear view of what's going on internally. We'll talk a little bit about performance and best practices specific to iOS. And I'll show you, and I'll promise you a lot more demos than this talk. There'll be a lot more interesting effects going on. And I'll give you an example near the end of how we can use OpenGL to apply some more fancy segue transitions for standard types of apps. And as a quick sneak peek at one of the demos we'll look at tomorrow using our favourite conference logo. But that's all. The code for this demo app is available open source and online. You can grab that and have a look at that. Thank you very much.